let's continue. Just to recap, at the end of the last lecture, we had this analogy with quantum states and probability distributions. And next, we can go into one of the main important theorems of quantum information, which is the no-cloning theorem. Here's a cloning box. It takes a quantum pure state, and it outputs 2 copies of that pure state. And in classical information, classical cryptography, classical computing, we take cloning for granted everywhere. Basically, if you have a string x, then you can compute 2 functions of x, like f of x and g of x, and those 2 functions and outputs can exist simultaneously, etc., etc., etc. Quantum mechanically, this box does not exist. So in general, it's not possible to copy quantum states. And this has consequences throughout the theory, as you can imagine. Actually, since we were in the pure state formalism and only talking about unitaries, this box is not really well defined because it maps 1 qubit to 2 qubits. If you want to formally define this cloning, you could input an auxiliary state, ket 0 for instance, and then ask for a unitary that would map unitary such as this one that would map u psi 0 to psi psi. And the theorem that we can state in the pure state formalism is that no 2-qubit unitary exists such that for all single qubits psi we have this cloning process. And the proof of this is relatively straightforward, so we can even go through this right now. It's by contradiction. Suppose that a u existed, and take, let psi be alpha 0 plus beta 1. Then u psi 0, it should copy psi, right? Make 2 copies. And then let's expand this in terms of the tensor product, and then you get this expression, alpha squared ket 0 0 plus alpha beta ket 0 1 plus beta alpha ket 1 0 plus beta squared ket 1 1. Also, if we take specific values of psi, for instance 0, then u applied to 0 0 should clone 0, so the output should be ket 0 0, and u applied to 1 0 should be 1 1 because it's cloned the basis state 1. So from these last 2 equations, by linearity, we could compute u alpha 0 plus beta 1 ket 0 in a different way, right? Above here, we've computed u psi 0 according to the cloning property, but here let's compute it according to the linearity property and these 2 lines here. So it would be equal to alpha u 0 0 plus beta u 1 0, and that would be alpha ket 0 0 plus beta 1 1. Here we have a contradiction because computing the expression in 2 different ways leads to 2 different values, namely this one here with these 4 terms and this one here with these 2 terms. So for instance, if you take alpha and beta being 1 over square root 2, you can never have equality between these two states, which contradicts the existence of this unitary u that would clone. So, actually, are there any questions about this, or even the first part of the lecture that I forgot to ask when we started? Does anybody want to go through anything that we've already discussed? Or does anybody have any comments on the no-cloning theorem? This is actually quite surprising. It seems like a huge disadvantage, but it also becomes a huge advantage, especially in cryptography. This brings me to the second analogy, which is quantum states as physical objects. Because of the no-cloning theorem, it's really useful to think as quantum information as being very precious, in the sense that an apple is very precious. If you have an apple, you only have 1 apple. You don't have 2. You can split the apple into pieces. You can share the pieces, but if I give away 2 pieces of my apple, I've lost those 2 pieces. I only have 4 remaining. And this principle appears everywhere in quantum information, and especially quantum cryptographers have really taken advantage of this. There's actually a way to think of cryptography in terms of, well, if I have a 2-party protocol, if I'm able to show that Alice has, so that say at the beginning there's an input, if I'm able to show that Alice has that input, then automatically we have tools of quantum information that tells us that Bob does not have that input. So that you have some ways to prove, to formally prove security by arguing about where is the information. Right, the information only existed in one single copy, so you can't copy it, you can't duplicate it, so if you're able to show that it's here, it's obviously not there. So that's our analogy in terms of physical objects. Physical objects are also very precious, you can't copy them, and that shows up in things like quantum money, where you want to have some quantum states that would represent bills or coins that you can actually exchange. And because of the no cloning, you can't, there's no straightforward way to, of course you have to formalize all of this, but there's no straightforward way to make copies of this information. And that gives you the property that you're looking for in terms of money and unclonability. So the next concept I want to introduce is entanglement. The definition is a quantum state is entangled over two subsystems. So entanglement is a property of two or more systems. So a quantum state of over these two systems, if it's entangled if it cannot be written as a tensor product between the subsystems A and B. For instance, this state here, it's a 2-qubit state. 1 over square root 2, 0, 0, plus 1 over square root 2, 1, 1. This is an entangled state. And it's one of the most commonly used entangled states. It's called an EPR pair after Einstein, Podolsky, and Rosen, and we also denote it phi plus. And to show that it's entangled, well, suppose that by contradiction that it would not be, that you could write it as a tensor product of two single qubit pure states. So this right-hand side, and then expand this right-hand side, you would have this superposition. And if you want to try to solve this, because it has to be equal to the left-hand side, you get these constraints. So this term here has to vanish, which means that one of these two is 0. Same thing here, this cross term, let's call it, also has to vanish. And then you get a contradiction, because these constraints mean that you can't actually have this left-hand side. So this state is entangled. The classical equivalent of entanglement is correlation. So don't be too scared about this word, it's a fancy word. It's a generalized type of correlation that you can apply to quantum states. So correlations means that you have two probability distributions and the statistics are correlated if you cannot express one system, or the two systems, the joint system, as the kind of product of these two independent distributions. So it's the same thing for entanglement. Two systems are entangled if you cannot write them as the tensor product of independent systems. There's some really interesting consequences of quantum entanglement. One of them is non-local games, or Bell inequalities. And at the end of this, if there's a little bit of time left, I'll go through some specific examples of these non-local games. And I'm sure that they'll come up later also in the context of device-independent quantum key distribution. And another consequence of this is teleportation, which is something that we're going to go through shortly. Are there any questions or comments about entanglement? Okay. So teleportation. Suppose Alice has a qubit, and she wants to send the qubit to Bob. But she only has a classical channel between her and Bob. So the question is, how many classical bits would be required in order to accomplish this task? Any thoughts? Yeah? Yes, it's a very good point. So the first answer is that this is impossible. If she could send this quantum state to Bob in a way that she can decode it into classical information, then she can actually copy it. So if she only has a single copy of this state, remember that there's no measurement that's going to extract alpha and beta. So she cannot actually extract alpha and beta and send them. Even if she could extract alpha and beta by some miracle, they're arbitrary complex numbers. So if she has a bounded type of only limited capacity on this classical channel, it's not clear that she can even do that, right? So two answers. Answer one depends on the desired precision. Alpha and beta are complex numbers, but Alice can send a approximation. Answer two, no number of classical bits will suffice, because she may not know the description of alpha and beta, right? This is a physical object, it's given to her, maybe she didn't prepare it, right? She doesn't actually know what it is. So she cannot perform measurement to extract these values. And then even another objection you might say is that this single qubit I've written here as a pure state, but it might also be entangled with some others, and then no amount of classical communication is going to be able to transmit that entanglement. So let's change the question a little bit. Again, suppose Alice has a pure state psi, and how many bits of classical communication would be required to extend this qubit to Bob if we allow Alice and Bob shared entanglement ahead of time? So what this means is that they have received a resource. Either they have combined their labs together in order to establish a shared entanglement, or somebody has given them these quantum correlations. And teleportation gives us a really nice answer to this question. It tells us that in the context where they share entanglement ahead of time, only 2 bits of classical communication are required. So, 2 bits of classical communication suffice for Alice to send the qubit to Bob, as long as they share entanglement ahead of time. And so this helps us understand the meaning of teleportation. So it sounds like a really fancy word. What it means is it's a way to transfer physical information, like qubits, for instance, from one location to another via classical means only. So they do need to, but note that they do need to share entanglement ahead of time. So there has to be some coordination ahead of time to have this resource. But after that is given in the setup, then the only thing they need is some small amount of classical communication. And here's a picture of the inventors or discoverers of quantum teleportation. I think it was a few years after their paper. It was a 1993 paper, if I'm not mistaken. So this is Charles Bennett, Bill Wooters, Richard Josa, Asher Perez, Claude Tempo, and Gilles Lessel. Oh yes, it's 1993. And in this slide we have a circuit. This is the first time that I'm presenting you quantum circuits. This is a very common method of describing a quantum process in terms of information processing. And this entire circuit, we're going to go through it, describes teleportation. So the first thing to know is that time goes from left to right in quantum circuits. So that means that the left-hand side has the input and the right-hand side has the output. So right away, since we're doing teleportation, you see the input here and you see the output here. And let's go through more detail on what's going on. We'll imagine that Alice has the first 2 wires. So each wire represents a qubit. Bob has the bottom wire. There's some other wires here. Double wires in quantum circuits represent classical communication. This M is a measurement, and these are quantum gates. So at the very beginning of the protocol, we have entanglement distribution. This brace here tells us that the first 2 qubits, they start in the entangled state, this EPR pair, 1 square root 2, 0, 0, plus 1, 1. So again, the entanglement, they could do this by planning ahead of time, getting together, doing some joint operation on 2 qubit system, and now they can separate and they still remain entangled, or somebody else can generate that for them and give it to them. Here's Alice's input qubit psi. So when you analyze a quantum circuit, we look at the state of the system at the different time steps. So if you start at this slice of time at the very beginning, we have the input tensor product with the entangled state, and then if we expand this, it would give this superposition of states for in general, we have a 3-qubit system in the circuit. The next gate that's going to happen is a control NOT gate. So this says that Alice, she has 2 qubits, and she should do this, remember this 2-qubit unitary that we saw? She should do this control NOT. This is the control wire, and this is the wire that undergoes the transformation. So if this wire is 0, nothing happens. If this wire is 1, then we have a bit flip here. So after the control NOT, which we denote control NOT tensor identity because nothing happens on the bottom wire, we have these bit flips that are going to happen. And then this gate here is the Hadamard. Remember, it was going to swap between the plus minus, the 0-1 basis and the plus minus basis. So Hadamard, tensor identity. And so we can write the effect of the Hadamard. Right, 0, 0, 0 goes to 0, 0, 0 plus 1, 1, 1, 0, 0. 0, 1, 1 goes to 0, 1, 1 plus 1, 1, 1, etc. So we have these 8 terms with these coefficients alpha and beta after the Hadamard. And the interesting thing is that we can rewrite this state at this time, right after the Hadamard, as by gathering the terms, because we're going to measure the first 2 qubits only. And remember, in the partial measurements, in order to know what happens when you do a partial measurement, you would write the state in terms of the basis states that are possible outcomes, tensor product with the remaining states. So if you, for instance, take out the 0, 0, then the remaining terms, if you take if the first 2 qubits are 0, then the third qubit is going to be alpha 0 from this term, and then beta 1 from this term over here. Hence here. For the first 2 qubits being 0, 1, then you would get alpha 1 from this term, and plus beta 0 from here, etc. And the thing to notice is that the remaining state after the measurement is a variant of the original state. Here we actually have the original state, alpha 0 plus beta 1, that was our input psi. Here we have alpha 0 plus beta 1 with the poly X, the NOT gate, applied to it, because you see the role of the 0 and 1 are inverted. Here we have the original state psi, except that there's this relative phase on the 1 state, so it's alpha 0 minus beta 1. So that's as if we had applied the Z gate, this poly Z, which, remember, swaps plus to minus and minus to plus. And here, we have both of these poly operators applied to the input, namely a phase from the Z gate and a bit flip from the X as an X gate. And knowing which one of these cases we're in, well, yes, we can know that because the measurement result, this says measure the first 2 qubits, Alice is going to measure the first 2 qubits, will tell us which operation we need to do. These are unitary reversible operations in order to actually recover the input qubit psi. So this is what these wires are saying. This says Alice measures the first her 2 qubits and then transmits using the classical communication channel those classical bits to Bob. And these are conditioned quantum gates. So if the wire here is 0, the gate is not applied. If the wire is 1, the gate is applied. So the circuit representation is meant to perform the corrections. So we can sometimes call these corrections. You undo these operations by performing the inverse, but the polys are self-inverse. So we simply apply the same operations in order to reverse them. And in all cases, you'll have reconstructed psi on Bob's side. So the interesting thing to notice is that the teleportation does not violate the no cloning, because when Alice does this operation of measuring, she has actually lost her ability to reconstruct the state psi. She's giving it away to Bob. And Bob, of course, can reconstruct it. The other interesting thing is a link with encryption, and this will be made more clear towards the end of the week, that these polys, these X and Z polys, They necessarily must be in the form of perfect encryption, because before Bob knows the measurement results, these 2 bits, there's no way that he can reconstruct psi, because that would violate relativity. Basically, it would allow instantaneous communication. So therefore, these polys must be a way to encrypt, kind of the same way that the one-time pad encrypts. This is a version of encryption called the quantum one-time pad. Okay, are there any questions about teleportation? Okay, so measurement, classical communication, classical controlled gates. Okay. The speaker is not working, but or maybe I just haven't figured out how to make it work. But there's some interesting videos. Actually, try again.
This was about a tantalizing paper from Wouters and Asher Perez that had showed that if you have 3 imperfectly distinguishable polarization states of a photon, for example, vertical and 120 degrees and 240 degrees, like we call it the Mercedes-Benz states, that in principle you can only distinguish 2 reliably, the perpendicular states, but if you have 3 that are 120 degree angles, they're not perfectly distinguishable. You're given 2 copies of this, and what Perez and Wouters investigated was how much better could you distinguish them by a complicated measurement than you could by a simple measurement. They found that you could distinguish them better by a joint measurement, by having them both in the same lab, than by doing separate measurements, even if you were allowed to talk back and forth and do very gentle measurements. I measure a little bit about this and I tell the result to the other person, and then they measure the other one, and then they talk back and forth for 20 iterations. It still isn't as good as having them both in the same place. And we were trying to figure out what is it that they don't have, that they need, that would enable them to do as well if they were in separate locations than if they were in the same location. And finally we figured out they needed some entanglement. So in other words, and it was pointed out even in the original Perez-Wouters paper that this effect was a dual to the phenomenon of entanglement. That is, in entanglement, 2 particles that are prepared in the same place behave in a strange way when you measure them separately. And here are 2 particles that are prepared separately, and yet you can find out more of them by measuring them together than by measuring them separately. So that duality was pointed out in the original paper by Perez and Wouters, but it was a paper that, it was a very stimulating paper, but it didn't solve the problem. It said, we don't understand why this is the case. So then we realized that by sharing entanglement between the 2 observers and by permitting them to communicate, you could simulate being in the same place. And we, of course, started sending emails to Asher Perez in Israel. And the rest of us were all exchanging emails right after this talk, because it was a stimulating conversation. And Perez was saying, well, it's as if one of the parties has some long-handled measuring tools that he can measure it even though it's not in the same place. And finally we realized what was happening is that by doing a joint measurement on one particle and one half of an entangled pair, you were recreating the state of that particle in the other lab. And I suggested the name teleportation for it. And Asher Perez said, oh, that is a barbarism. It's mixing Greek and Latin roots. You should stick with the Greek root and call it telephoresis. But the other people all like teleportation better, so we stuck with that. One of our colleagues who was talking to us much of the time but wasn't actually working on this one was Ben Schumacher, and he said, well, I'm glad I'm not part of this because you've given it a name that will produce all kinds of misunderstanding.
Okay, and then there's also another video, which I think I'll skip for now, but on the meaning of teleportation by Gilles, and he compares it to Star Trek. Actually, I have a little bit of time, which is fantastic, because I also wanted to give you another appreciation of entanglement. Okay, so this is another consequence of entanglement, and these are non-local games, which gives you a kind of combinatorial way of understanding the power of the correlations that entanglement can give. So this is via a game. We'll define a magic square to be a matrix of bits, 0, 1. It's a 3 by 3 matrix. These are not the magic squares that you may have heard about in mathematics. These are different. They have the property that if you take the sum of the bits on each row, then you'll get an even number, such as in this case. And if you take the sum of the bits on each column, then you'll get an odd number, such as this case here. And the first question that you might ask is, does a magic square exist? So this is not a magic square because the sum of the third column is even and it should be odd. Right. So there's a problem here, there's like a conflict, but if you flip this bit to be 0 to fix the column rule, then this row becomes odd, which is also not allowed in a magic square. So basically, is there a way to fix this, or is there a problem here? Is what you might wonder. So does anybody have an idea? Magic square might exist? Yes, very nice, thank you. It's not going to exist in general if you put arbitrary values for these entries, and if you take the sum according to all the rows, then you should get an even number because all the rows are even, but if you take the sum according to all the columns, then you should get an odd number because you have an odd number of odd columns. So the magic square doesn't exist, I get that. I guess that's why it's called magic. Based on the magic square, we're going to define a game. We have a referee and Alice and Bob. This is a cooperative game, or also called a game of coordination, I believe, where Alice and Bob, they play a game, but they want to win together. So they want to collaborate in order to win this game. It's basically as if they're playing against the referee. But they're separated, they can't communicate. They'll be given questions. Alice is going to be given a row, for instance, row 1, and Bob is going to be given a column, for instance, column 3. So these are the questions they get from the referee, and then they must answer. So Alice must answer a row, for instance, this row, and Bob must answer a column, for instance, this column. And then the referee decides if they win or if they lose. In order to do that, he places the row and the column that he received in a magic square, namely row 1, because he said row 1, and column 3. And he checks the row rule, the column rule, and the intersection. So in this case, they win because they satisfy the parity of the row, parity of the column, and the intersection here, 0, it has to agree. So they've won. Here's a situation where they would lose. So if they answer like this, row 1, column 3, the intersection, the column rule doesn't satisfy because he's answered an even column. So they lose. So then, what's the best probability of success that the players can achieve in this game? Where we specify that the questions are asked uniformly at random. First of all, can they always win at this game? If they always win, they always have to satisfy the row rule, the column rule, and the intersection. But such a winning strategy corresponds to a magic square. If they were to always win, they would actually have to have a magic square in mind and answer according to that magic square, so they can't always win. What's the best they could do? Well, they could win on 8 out of the 9 possible questions. For instance, Alice has this square in mind, and she answers according to these rows. And Bob has this square in mind, and she answers according to these columns. And the only question on which they're going to be caught, i.e. the intersection is not going to agree, is on question row 3 and column 3, because of this entry here. They can also have a probabilistic strategy. So they get together ahead of time, they flip coins, or they share a string generated randomly, which tells them a distribution, a probability distribution on these deterministic strategies. But that's not going to help them win with probability more than 8 knights. So, as a hypothetical situation, imagine you were the referee, and you were playing this game, and that you saw that Alice and Bob were always winning. You might wonder if they're cheating, so then you use the laws of physics. You might place them in distant galaxies and look at the timing of your questions to make sure that they're really not allowed, they're not able to communicate. Even the laws of physics, i.e. relativity, prohibit them from communicating. And then they keep on winning still. Are they being really lucky? So if you, maybe for a few rounds, they're being lucky, and that you're not observing these events where they're going to lose. So then you keep on repeating this until the probability of winning would be really, really small, and they keep on winning. So then you wonder, well, maybe there's laws of physics that might actually allow such a winning strategy. And then, of course, since we're here talking about quantum information, you upgrade your knowledge of physics from the classical information to quantum information, and then you realize that by sharing entanglement ahead of time, there's actually ways for Alice and Bob to achieve correlations that are stronger than what's achievable using probabilistic strategies only. Okay, so unfortunately this quantum winning strategy is a bit complicated to explain, but if they share this entangled state, so this is a 4-qubit entangled state, each party is going to have 2 qubits, and these are the conditional transformations. So if Alice receives question 1, she applies this unitary on her 2 qubits, question 2 this unitary, etc. And Bob also applies unitary depending on his input, question 1, question 2, question 3. Then you can show that they will end up still in a superposition, but these terms in the superposition are nicely coordinated so that when they measure, they have equal probability of measuring these possibilities, and then they complete their 3rd bit in terms of the parity rule. They will actually have a winning strategy because when you put these values into the columns and the rows, they will perfectly match up. So for instance, for the case r equals 1 and c equals 2, using the entanglement, Alice and Bob are going to appear to be sharing these partial magic squares with equal probability, and all of these are correct. They all have the column rule, the row rule, and the intersection. So that's one example of how quantum information can help in these non-local games. And they're going to win perfectly. Here's a second game where they also win perfectly. It's the GHZ game, and this one has a strategy that's easier to explain. It's a 3-player game. It's called the Mermen Jeeves game. You have Alice, Bob, and Charlie. And here they get inputs which are single bits, with a promise that the sum of the inputs is even. And then they must answer also a bit each. And the winning condition is that the parity of the outputs should be equal to the sum of the inputs divided by 2, or the parity of the sum of the inputs divided by 2. Since the sum of the inputs is even, then this is still an integer. And similarly as in the magic square game, there's a simple logical argument to say that there's no classical winning strategy. Because if they have these pre-assigned values where A0 is the value that Alice answers if she gets input 0, etc., B0 is the value that Bob answers if he gets input 0, then we have to have that these 4 equations are satisfied. And again, if you take the parity of, if you add all these equations, you'll get the right-hand side being odd and the left-hand side being even because each term appears exactly twice. So you get a contradiction. So there's no classical winning perfect strategy. But quantumly, if they share an entangled state, namely this what's called the GHZ state. So this is related to the EPR state that we had, the 2-qubit state. This is a 3-qubit entangled state, 0, 0, 0 plus 1, 1, 1, and it's entangled. Then the strategy is simply to apply, this is in the R theta, this is a unitary in the R theta family, 1, 0, 0, I, and if your input is 1, you apply this unitary transformation. And what happens is that it puts this relative phase, but each player is contributing this conditional relative phase depending on their inputs. So these I's will multiply together. And then each player applies a Hadamard transform. And the result is that if you have an even number of players doing this operation, you'll get this superposition of even bit strings. And if you have an odd number of players, you'll have this superposition of odd bit strings, which is exactly what you need to do in order to win this game perfectly. So they have this entangled strategy that's going to win perfectly. And I think I'll skip that. Okay, so now we've talked about entanglement and two phenomena, basically teleportation and non-local games, and how entanglement can help in these two contexts. So, as a conclusion, and my understanding is that these slides are also available on the Winter School website, so you can always go back and refer to these. I wanted to give you some references. There's a few quantum information textbooks that might be of use if you're wanting to know more about quantum information. So Nielsen and Chuang is from the year 2000. They wrote, this is still one of the main references for quantum information. But perhaps a little bit more relevant from the computer science and mathematics point of view are these last two, which are Introduction to Quantum Computing by Phil Kay, Ray Laflamme, and Mike Maska, and Quantum Computing, a Gentle Introduction by Eleanor Riefel and Wolfgang Pollack. And I also have a slide with, I also have a slide with online references. So lecture notes of Ronald de Wolf at CWI are a nice way to learn about quantum information and algorithms. And John Watrous has two sets of lecture notes, one that are more introductory and ones that are also more advanced from a mathematical point of view. There are at least two textbooks that are relevant that are also available online. Mark Wilde has a book on quantum information theory, and John Watrous has a book on the theory of quantum information, which is a very recent book. If you're not familiar with the preprint server, so in cryptography there's the ePrint server where people put their preprints. In quantum information, most papers are posted on the archive under QuantPH. And there are at least 3 wikis that are relevant. Quantum Algorithms Zoo is a compendium of all the known quantum algorithms. Complexity Zoo has classical complexity and also quantum complexity. And there's a wiki called Quantiki that might help you understand the complex landscape of quantum information. So I'd like to thank you for your attention. And I'd be happy to take any questions.